Hello, my name is Marco Donat and I'm working at Leibniz Center for Agricultural Landscape Research in the working group Resource Efficient Cropping Systems. Today I would like to give you a small insight into our work on a tool that will facilitate the implementation of small-scale and site-specific farming. With small-scale and site-specific cultivation, I mean the concept patch cropping, which I would like to explain now. The first step is to analyze the field for its site-specific characteristics and then subdivide it. The divisions created in this way makes it possible to divide the field into patches with different yield potential. Areas with lighter conditions, we call it areas with low yield potential, in this example the orange polygons with sandy soil, can be planted with crop varieties and crop rotations adapted for these sites. In areas with better soil characteristics, the green polygons, here with loamy sand, crop varieties and crop rotations can be planted which are adapted to better sites. These areas have higher yield potential. The redesign of the fields based on this concept results in the change of the field size and shapes. The effects of field sizes have long been studied in the areas of basic ecology and applied ecology, and because of their effects on biodiversity, new concepts of agricultural landscape design have been requested. This figure here on the right shows how the increase in the number of crop species on the x-axis and the reduction of field size on the y-axis leads from simple landscapes to complex landscapes with a temporal and spatial diversification. These complex landscapes have positive effects on various ecosystem services and lead to a more resilient ecosystem. But how can we implement patch cropping in practice? The idea so far is that in the future robots will be able to manage even small subfields profitably due to autonomous navigation and the resulting elimination of labor cost. However, ideally, this cropping system should be started today, with today's technology and under today's conditions. There are of course some problems and restrictions if we want to implement this cropping system today. In Brandenburg, for example, agriculture subsidies are only available for subfields of 0.3 hectares or more of uniformly cultivated land. On the other hand, today's farmers have large machines with maximum working width. This has to be taken into account. There is also the question of how exactly to deal with isolated patches, for example when a patch is in the middle of the field. And of course this system will be associated with higher costs today, as the machines have to be driven over much more frequently, and more frequent turning maneuvers can also lead to soil compaction. And because we already want to work on the possible implementation of patch cropping, the idea was to provide farmers with a tool that analyzes the heterogeneity of the field and provides georeference patch cropping maps. Heat maps are very helpful for heterogeneity analysis, but also contain a lot of analyst data points. Here you can see the field and the yield data points from 2015. Red points represent data points with low yield values. Green points represent data points with high yield values. There are a lot of different errors. Header width error, end of row error, extreme yield values, filling time error, and positioning error. This is the reason we have to use different filters to clean the yield maps from erroneous data points. Here you can see our workflow we have implemented. This left part here is about the correct processing of the yield maps, filtering of erroneous data points and interpolation of the yield values. This right part is about the creation of the patch structure and the cluster analysis. I will now introduce the most important things in detail. The first processing steps are the calculation of the yield to standard moisture content. Data points with a moisture content or yield value of less than 1 are removed, and data points with a harvester header width smaller than 1 and sun speed changes greater than 2 km per hour are removed. The next step is the removal of all data points near the edge of the field boundary. With this, we remove all data points which are in the end of row area and which can hold faulty data points. At the same time, we also remove all data points that could have been influenced by the edge effect, shadows, soil compaction in the heatlands, and varying of input. We used a 40-meter buffer for the removal of the buffer area, as this was slightly larger than the maximum working width of 36 meter used by the farmer. Unfortunately, a lot of information is lost with this step. Global outlier are data points with yield values that lies outside the general range of the dataset. Therefore, we have calculated a z-score for each data element, zi. This score results from the yield value, xi, minus the mean of the distribution, divided by the standard deviation of the distribution. This expresses that as deviation from the mean relative to the standard deviation. Data points with yield values plus minus 3 times the standard deviation were removed. After global outlier removal, we removed spatial outliers. These are data points with yield values which significantly differ from the yield values of its neighboring data points. The first step is to determine the neighborhood. We decided on a neighborhood of a radius of 40 meters around the data point to be checked. This results in a relatively large neighborhood, but also includes data elements from several neighboring rows. This is especially important if more than one combined harvester was used at the same field, resulting in distances of more than 20 meters to the next neighboring row. First, all local neighbors had to be identified for each data element. Then, for each data point, the local Moran index was calculated. Data elements with a significant negative local Moran index were removed. In order to be able to compare the yields of the individual years, the yields must be standardized. The yield of the data points is divided by the mean value of all data points and multiplied by 100. For the interpolation, we first created a grid and then computed the experimental diagram. Spherical and exponential models were used to fit the experimental diagram. The model with the lowest residual sum of square was used. Right here you can see how the interpolated standardized yield map of 2011 looks like. Yellow and light areas are yields above the average. Dark areas are areas with yields below the average. After the cleaning and interpolation step, we create the patches. For the patch generation, two things have to be considered. On the one hand, we want to use information of the controlled traffic farming system, which is a permanent track that the farmer is using for years and for all operations. And on the other hand, the maximum working width should be considered, which is usually defined by the field sprayers and fertilizer spreaders. The usual working width of the controlled traffic farming system is 10 to 36 meters, which means that if rectangular patches are made, it must be a multiple of the maximum working width. The run line consists of a georeference line with two coordinates. We use these points to generate a patch structure of, for example, 72 meters, which is parallel to the run line. The patches are oriented on this track in such a way that the patch can be processed twice with a maximum working width. Here you can see the run line, which is parallel to the lower edge of the patch with a distance of 80 meters. The next step is a cluster analysis. For this, we have merged all the yield maps and calculated the average of all maps per patch. Patches containing less than 30% of the data points were not included in the analysis. For the cluster analysis, we use the fuzzy k-means algorithm. This is a soft clustering method. Each data point can belong to more than one cluster group. All the input data were analyzed without weighting. The number of cluster groups was set to 2, since we want to divide the field into areas with high and with low yield potential. As an output, we produce different georeference maps with 2 or 3 cluster groups and with different patch sizes. Here, for example, we have 2 cluster groups and patch sizes of 72 meters. The numbers within the patches are the membership degrees and give us information about the membership of the patches to the cluster group 1. Here synonymous to high yield potential. The green patches. This membership degrees can assume values from 0 to 1, where small numbers mean that this patch belongs to cluster group 1 to a low degree. Numbers close to 1 indicate a high degree of membership in cluster group 1. This is an advantage of the fuzzy k-means clustering algorithm because we receive additional information about the degree of the membership of the individual patch to the respective cluster group. Here I would like to introduce a prototype which illustrates the function of the web app. You can see the yield maps of the individual years. If you click on Analyze, patch cropping maps are generated. You can click through and choose the most suitable map and download it. Finally, I would like to give you a short outlook. This is our prototype at the moment, which uses widely distributed data to classify the field into yield potentials and produce georeference maps. However, the farmer does not yet know how to best manage these patches. We are currently working on a path planning algorithm that will calculate the most efficient route for each patch cropping map, thus reducing resource consumption and labor requirements. It is also not yet clear to which yield potential the buffer area should be allocated. Removing the buffer area is good for removing the erroneous data points, but with that we lose around 1/4 of the whole dataset, which is also depending on the size of the field. We also plan to include the possibility of adding additional information and data that can improve the accuracy of the analyzers, such as electrical conductivity data or digital terrain models and indexes derived from them. Furthermore, the annual variability of yields has not yet been taken into account, which we plan to do by adding another class, the inconsistent yield potential.